Hey guys, it's Miss Maneely again, and I am here to help you along with the last and final section of your Algebra 2 quarterly assessment review. And this tutorial is going to focus on polynomial functions. So if you take a look at number 10, you'll see that you're given in a situation where a polynomial function has zeros at x equals, and then you'll see brackets with a 0, -1, and 2. This is set notation. And all it is doing is it's simplifying, instead of writing our solutions as x equals 0, x equals -1, and x equals 2, it simplifies it to sort of group everything together. But notice that we're not using parentheses. Parentheses would indicate that it's an ordered triple. When we use this notation, it's considered set notation, and it's basically giving us all the values that x can take on. And so if I have 3 zeros for my function, and I'm asked what the degree of the polynomial is, since I'm not really given any information about multiplicity, I'm going to assume that each of those zeros is a single root. That means that if I had 3 zeros and they're all single roots, my degree must also be 3. All right, and then in letter B it says to assume that the leading coefficient is a equals 1, and you're asked to write the equation for the polynomial in factored form. And remember, factored form, just like with what we did with quadratics, is basically when you have all the parentheses. Well, with quadratics, I had 2 sets of parentheses. If I'm dealing with a polynomial of degree 3, I'm likely going to be able to write my polynomial using 3 sets of parentheses, or 3 factors involving x. So I know that the leading coefficient is 1. That would be the number out in front. And then if I take a look at my first root, or 0, at 0, I know that when I write something in factored form, actually let's just do that up here, it's going to be of the form a times x minus p times x minus q, and so forth. If it's a polynomial, obviously I can have more factors than that. But remember, we're always taking the opposite of the root when we put it into the factored form. And that has to do with the zero product property, setting the factors equal to 0 and solving. So if I have a root at 0, that's the same thing as saying x minus 0. If I have a root at x equals -1, when I end up putting that into my factor, it's going to be x minus a -1, or simply x plus 1, because minus a negative is the same as a plus. And then my last one would become x minus 2. Now let's go ahead and simplify that. I don't really need to show the 1 out in front. And when I think about x minus 0, that's just x. So let's just go ahead and write it as x. This is going to be times x plus 1, and then x minus 2. The next thing you're asked to do is to write the polynomial in standard form. So most of us are used to multiplying 2 things at a time, a binomial times a binomial, or distributing a single term, like a monomial to a binomial. In this case, we have 3 things we need to multiply. I'm going to start by multiplying my 2 binomials together. And we can use FOIL, or we can use the box method, as you saw in the second tutorial on quadratic functions. So I'm going to leave that x out in front. In fact, I'm going to go ahead and use the FOIL technique. I'm going to leave the x out in front, and I'm just going to focus on these 2 factors, x plus 1 and x minus 2. And so let's just focus on these 2. I'm going to go ahead and multiply my x times x, and that's going to give me x squared. I'm going to go ahead and multiply my outer terms. X times -2 is -2x. My inner terms, it's going to be 1 times x, or simply x. And 1 times -2 is going to be a -2. And I do have to remember that there's still an x on the outside here. But let's go ahead and combine my like terms. So I'm going to still have the x on the outside, and I'm still going to have this group of terms. The only terms that I can actually combine are going to be the -2x plus x. And again, that's just a 1x, and -2 plus 1 is going to give me a -1x, or simply -x. So I'm going to have x squared minus x minus 2 in my parentheses. And then the last thing I need to do is multiply x times that quantity. And this I can just use the regular distributive property. So x times x squared, that's going to be another factor of x, so it's going to increase my exponent to a 3. And then x times -x is going to give me a -x squared. And then x times -2 is going to give me a -2x. So a couple things, if this were, say, like a multiple choice question, a couple of things that I can do to simplify and to kind of understand what my answer is going to look like. I already know that it's degree 3. So if I have any answer choices that don't have an x to the third power as the leading term, then I can eliminate them as my answer choices. So if you see an x to the 5th or an x to the 4th, you can rule that out as an answer choice. So you only want to limit to the x to the third power. And that might help remove some of your answer choices. All right, let's take a look at number 11. It says a discount sports store opened in 2000. The annual revenue for several years is shown below in the table. And it says for this time period, the store's annual revenue, which is R in millions of dollars, can be modeled by the function, and you're given an equation where T represents the number of years since 2000. You're asked to use the model to estimate the year in which the revenue amount reached $8.2 million. So one of the things I have to pay attention to is this value here of T. T represents the number of years since 2000. So if I think about it, this is similar to the problem that we did with the electric bill, where we assigned T to represent the number of months since January. So if I were to add like another piece to my table here to include the actual value of T, in 2002, that's 2 years after the year 2000. So that would give me a T value of 2. In 2005, T would be 5. In 2009, it would be 9. In 2012, and then in 2015. And so now I have some frame of reference for what the values of T are that I'm going to be entering into my calculator. In letter A, it says to use the model to estimate the year in which the revenue reached $8.2 million. So I need to think to myself, is 8.2 going to be a T value or an R value? And in this case, it's telling you that it's revenue. So that's going to be an R value. Now, in our calculator, we don't use T and R, we use X and Y. So if it helps you to kind of think about this equation in terms of Y equals, that's going to be an X to the third, this is going to be an X squared, this is going to be an X, and so forth. You can do it that way as well. And this time, X would represent the number of years since 2000, and Y would represent the revenue. So if I know that my revenue is 8.2, I can think of that as a Y value, being 8.2. Oops. Okay, so if Y is equal to 8.2, and I also have an equation for Y, what I'm going to do is put these values into my calculator. So anytime you have a Y equals, the place to go on your calculator is your Y equals menu. So I'm going to go ahead and type in both things. I'm going to type in my equation where I've got the 0.001, and then in parentheses. Now again, I don't have a T, so I'm going to use X instead, and I'm going to have a negative X to the third power. And so I use that upper caret. That's going to move my cursor into my exponent where I can type in the 3. Just make sure if you have one of the newer calculators that you move the cursor out of the exponent before typing in the rest of your equation. Then I'm going to have plus 16. Again, I'm going to use an X. This time I'm going to just use my X squared button. Plus 900X minus 1400. And then I'm going to go ahead and close my parentheses. And then I'm going to have another equation for Y equals 8.2. Because in a situation like this, it's going to be hard to solve that equation algebraically. So it's going to be a lot easier if I just go ahead and construct a graph. The trick, though, is coming up with an appropriate window for your graph. You could certainly enter the data into your calculator and then do a zoom 9 to set up a scatter plot. I'm actually going to turn my plot off, actually, so let me go ahead and press enter for that. If I want to construct a graph, I really just have to pay attention to the X and the Y values. And remember, we said that X is going to correspond to T and Y is going to correspond to my revenue. So if I go to my window, I can see that the minimum X value is 2 and the maximum X value is 15. So I'm just going to go a little bit beyond my min and my max and go from like 0 to 20. And if I need to get bigger than that, I will. And then when it comes to the revenue, I can see that it goes from 0.5 to 12.3. So again, I'm going to go a little bit beyond that, and I'm going to go from 0 as my minimum to 20, again, as my maximum. And then I'm going to go ahead and hit graph. And what I'm looking for is where these two equations intersect. And as long as I can see the point on my graph, the calculator will actually determine that for me. So I'm going to go ahead and hit second, trace. That's my calc menu, and that's going to let the calculator determine the point of intersection. And that's command 5. And when you're using the intersect option, you really just have to find the intersection, move your cursor as close as you can to that point, and then press enter 3 times, because it asks for the first curve and then the second curve, and then it asks you to guess, which is kind of silly in my opinion. And so when you solve this time, you're looking for the x value, or let's go back to the variable we're using in this equation. We get t is equal to 10. And that's going to be, again, 10 years after 2000. And so 10 years after 2000, the question is asking what year will this happen? So 10 years after 2000 would be the year 2010. In letter B, it says for t equals 12, what is the residual? And it's very important on the exam that you guys remember what a residual is. It's the difference between the actual value. So the actual value in the table is 9.9. It's the difference between that and what the equation will predict when t is 12. And so this time I don't need to use my graph. I can actually do this on my home screen. To find the prediction, I'm going to type my equation in. So 0.001. And then in parentheses, I'm going to have a negative. This time, though, I'm going to let t equal 12. So instead of typing in an x to the third, I'm going to put in the 12. Again, I'm going to do this in parentheses. And I'm going to raise it to the third power. And then I'm going to move my cursor out so that I can type in plus 16. And then in parentheses, I'm going to put in 12. And then that is squared. And then I'm going to put in plus 900 times 12 minus 1400. And then I'm going to close my parentheses. And when I press enter, that's going to give me the estimate, or the prediction that my equation produces. So the actual value, a residual, remember, is, whoops, okay, so the residual is the actual minus the predicted. And we already said in the table, the actual value is 9.9. And I just calculated my prediction, which is 9.976. And so I'm going to subtract this on my calculator. Make sure that you subtract in the correct order. So 9.9 minus 9.976. And I'm going to get a negative 0.076. And that's the residual. And if I asked if the residual tells us if our model is appropriate or if our estimate is close, you're just looking to see how far off our estimate is. We obviously don't want there to be any error. We want our predictions to match the values in the table. So we want our residuals to be very close to 0. In this case, it is. Negative 0.076 is very, very close to 0. And so I would say that we can be pretty confident in our estimate. Okay, in number 12, it says, suppose the area of a flag is represented by the function a is equal to 2x squared plus 9x plus 10, and x plus 2 represents the length of the flag. You're asked to use synthetic division to determine the width of the flag. So if you think about the formula for area is equal to length times width. If I know the area and I know the length, and all I want to figure out is the width, if I divide the area by the length, then I know I can determine the width. So that's essentially what we're doing. We're taking the area and we're dividing out the length. And there is a process of long division if you want to use it, or we talked about using a process of synthetic division. When we use synthetic division, though, you have to figure out what the 0 of the function is. And if x plus 2 is a factor, then x equals negative 2 is a 0. And what I want to do is I want to put that on a shelf. The next step is to list all of the coefficients of your function a. And so it is in standard form. I'm not missing anything. So I've got my x squared, and then it's x, and then it's the constant. So all I'm going to do is write my coefficients and my constant in order. So that would be 2 9, and 10. I leave a little bit of space and I draw a line. You always want to bring down the first term exactly as it's written. And then we multiply. Negative 2 times 2 is negative 4. The next step would be to add. So I've got 9 plus a negative 4, which is a positive 5. And now I multiply again. Negative 2 times 5 gives me negative 10. And when I add my 10 to the negative 10, I end up with 0. I'm glad that it's 0 because this expression right here represents my remainder. And if you were doing this problem and you ended up with a remainder, in this particular case, because you were asked to find the length and the width, having a remainder would indicate that you probably made a mistake. So in this case, I ended up with 0 remainder, which means that x plus 2 divides evenly into my area function. And it leaves me with this expression here. Well, this expression can be written as a binomial. So remember, we started off with x squared, and this was x. But I factored out an x. So if I divide out an x, that means I no longer have x squared. I just have a single factor of x plus 5. And so that's what expression is left. The length then would equal 2x plus 5. And if you're not sure, you can always multiply it back. So x plus 2 times 2x plus 5. If I were to FOIL this back out, and you're not asked to do this on the problem, but if you wanted to check your work, x times 2x is going to give me 2x squared. X times 5 gives me 5x. 2 times 2x gives me 4x, and 2 times 5 gives me 10. And when I combine my middle terms, I get the 9x again. So if you've done it correctly, then you should be able to multiply the two factors and end up with the expression that you started with. That's a quick way to check to make sure you did it correctly. Again, on this problem, if you end up with a remainder, it doesn't make sense for this particular problem to have a remainder. But if you did, for other problems, then you would just write it as a fraction over the quantity x plus 2. All right, numbers 13 and 14 are simply matching. And notice that you are not supposed to use a calculator. We've been able to do most of these problems without a calculator, actually. So that's a good thing. In number 13, it says to describe the end behavior for each polynomial function and then match each equation to its graph without using a calculator. So let's take a look at the first one. The function is y equals negative x to the fifth plus 6x to the third minus 2x plus 4. I can see that that equation is in standard form. So the only thing I really want to look at is that leading term. The fact that the degree is odd, that's the 5. So I've got the degree is 5. That must mean that it's an S-shaped graph. The fact that the leading coefficient is negative tells me that my function should be S-shaped and should be decreasing. So in terms of the end behavior, and please again note that the way the end behavior is written, we look at how x is approaching positive infinity first. That means that we're going to look at the right side of the graph and then the left side of the graph. So if I look at the right side of the graph, I can see that it's pointing down towards negative infinity. And if I look at the left side of the graph, it's pointing up towards positive infinity. Well, if I take a look at my options, there are actually two functions that behave this way. So I've got to figure out another way to differentiate between which is going to be the graph for the first one, C or D. The other thing that you should consider when you're looking at the degree is the number of turns that the function can have. And if the degree is 5, that means that the function can turn up to 4 times. So if I take a look at the graph of C, let's just follow it with my pen. It's decreasing, and then it turns. So that's the first turn. It's increasing, and then it turns again. So that's the second turn. It decreases and then turns. That's 3, and then 4. So this has 4 turns in it. That means that its degree has to be at least 1 more. So that means that letter C is going to correspond to my first equation. If I take a look at letter D, I can see that it decreases and turns here. So that's 1 turn, and then it turns again. So this has 2 turns. That means that it has to be at least degree 3. So degree 3 or more. This one would have to be degree 5 or more. And while we're at it, let's just go ahead and take a look at the other ones. With letter A, it turns here, so that's 1, 2, 3. It actually looks very subtle, but it looks like it might turn here as well. So 1, 2, 3, 4. 4 or 5, it's hard to tell. I guess it's 5. So 1, 2, 3, 4, and 5. So if there are 5 turns, that means it would be degree 6 or more. And this last one, it's got 1 turn, 2, 3 turns. So that means the degree could be 4 or more. All right, so let's take a look at the next one. The next one is y is equal to negative x to the third minus 2x squared. So again, I'm looking at that leading term. The exponent is odd, so that tells me it's going to be an S shape and it's decreasing. And so again, that's going to have that S shape that decreases. There's only one more like it, so I know this has to be the graph of D. And it's going to have the same end behavior as the equation above it. So if I look on the right, I can see that my graph is going down to negative infinity. And if I look on the left, I can see that my graph is going up towards positive infinity. If I look at the next one, we've got y is equal to 5x to the fourth plus 10x to the third minus 2x plus 1. So my leading term is 5x to the fourth. The degree in this case is 4. It's also got a positive leading coefficient, so that tells me it's going to be opening up and it's going to be going up in both directions. So it's going to look like a parabola that's opening up. There's only one function that does this in terms of my graphs, and that would be letter B. And now if I take a look at the end behavior, as x approaches positive infinity, that's on the right, and my graph is going up. As x approaches negative infinity, that's the left, and I know my graph is going, whoops, my board stopped calibrating on me. Sorry, I can't reach my pause button, so you're going to have to wait while I calibrate. I apologize. Okay, let me see if I can fix this. Okay, so if I'm looking at that second, as x approaches negative infinity, again, we're looking at the graph of B. It's also going to positive infinity. I don't know what's wrong with this thing. All right, and then obviously that leaves the last graph as my negative x to the sixth power. That's going to be an even power function that is decreasing, so both ends should be pointing down. That's going to correspond to the graph of A. I'm sorry about my my smart board. I don't know what's happening. And since both ends are going down, it doesn't actually matter if you look at the left or the right-hand side first. But if we look at the right side first, that's as x approaches positive infinity. I know that x is approaching negative infinity. And on the left side, as x approaches negative infinity, the graph is going down towards negative infinity as well. Okay, let's take a look at the last problem. This time you are given the functions in factored form. And this is when it's really important to pay attention to not only the root, but the multiplicity of the root. And so remember, if we have a single root, let's see if I can actually write on my smart board. Let me try recalibrating again. I can't hit anything. Okay, so if we have a single root, the graph is going to pass straight through it. I don't know what's wrong. So if I have a single root, my graph is going to just kind of pass through the x-axis. If I have a double root, this is really funny, my graph is going to have like a turning point. Pretend that actually intersects. It's going to turn on the graph, and that's going to be a double root. It's going to, when I say turn, I mean it's going to change directions. It's going to go from decreasing to increasing or increasing to decreasing. And if I have a triple root, I don't know what's happening to my smart board. There we go. If I have a triple root, what you're going to see is a point of inflection. That's not happening on the graph. but you're actually going to see where the concavity changes. So if you look at example A, if you look at that graph, the very first x-intercept you see at -2 has a point of inflection at -2. So that's actually going to be a triple root. So I'm not sure which is going to be easier, if you identify looking at the graphs first or if you look at the equations first. I'll look at the equations first for the first, and then I'll do the same thing with the graphs. So in the first one, I can look at the factors. I see I've got a negative x minus 2 times the quantity x plus 3 squared. If I look at that, I can see that I have one factor of x in my first factor, and then the second factor is squared. So that means that this polynomial is degree 3. So that gives me a hint that it's going to be an S-shaped graph. The fact that it's negative tells me that my S should be decreasing. So that's important because that's going to rule out like A, it's going to rule out C and D. It's actually going to rule out everything but B. I mean, if I look at just the degree and which direction it's going, I can actually identify the graph just from that. So I know my answer is going to be B. The other thing that you want to look at is the roots and the multiplicity. So if I look at this first factor, that x minus 2, that means that I'm going to have an x-intercept at positive 2. The fact that this factor occurs once, even though you don't see that exponent, that tells me it's a single root. So it's going to pass straight through. And that is what's happening here on B. If I take a look at the second one, I've got x plus 3. That tells me that I'm going to have a root at -3. The fact that it's squared tells me it's going to be a double root. And so if I take a look at B, that's exactly what I see. I see at -3, the graph actually turns. So whether you're looking at the actual x-intercepts and their multiplicity, or you're looking at the long-run behavior of the graph, I can see either way that first equation is going to correspond to the graph of B. I'm going to go ahead and check it off. Let's take a look at the next one. This time I have x plus 2, the quantity cubed, times x minus 3. If I count up all the factors of x, since that first one is cubed, that's a triple root. If I add in the other factor of x, that means I'm dealing with a function with degree 4. Since the leading coefficient is positive, I know from far away my long-run behavior is going to look like both ends are going to be pointing up. So in this case, I do have a bunch of different graphs to choose from. It could be A, it could be C, or it could be D. So I've got to be able to narrow it down a little bit more, so I have to look a little bit more closely at the roots and the multiplicity themselves. So if I have an x plus 2, that tells me that I have a root at -2. Since that's cubed, that tells me it's a triple root. So at -2, I'm going to expect to see that my graph changes concavity. And so if I look at A, I can actually see right here at -2, that's a triple root. The graph changes concavity. If I look at C and D, I'm not seeing that. So let's double check to make sure that the rest of this works. If my next factor is at x minus 3, that means I'm also going to have a single root at x equals 3. And that's exactly what I see in letter A. So A is going to correspond to my next graph, and I can cross that off my list. Let's take a look at the next one. I've got x minus 2, the quantity squared, and x plus 2, the quantity squared. So altogether, I'm going to have 4 factors of x. So again, I have degree 4, and so that leaves me still with options C and D to choose from. So if I take a look at my first factor, I've got x minus 2. So since it's squared, that means that x equals 2 is a double. And if I look at the next factor, that means that x equals -2 is also a double. If I look at the graph of C, I can see that there's actually 4 distinct roots, so that's not going to correspond to my graph, or to my equation. But in letter D, I can see that I have a double root at -2 and a double root at +2. So D must be the correct graph for that third equation. Let's take a look at the next one. This is a little different. I have one factor of x here, another factor of x here, and even though this quantity isn't being squared, if you look inside, you can see that there are 2 factors of x inside. This is another function of degree 4, and this one's opening down. So I'm going to still have that U-shaped graph, but both ends are going to be pointing down. And if I look at my options, I can see that the only option is G. So I know that that's my answer. But let's take a closer look. The factor at x minus 4 tells me I'm going to have a single root at 4, which I do. The factor of x plus 4 tells me I'm going to have a single root at negative 4, which I do. This factor here, x squared plus 4, notice how that I don't see the graph crossing the x-axis again. That must mean that the quantity x squared plus 4 corresponds to imaginary roots. And you may ask yourself, how in the world am I supposed to know that? Well, remember, when we're finding the zeros of functions, we're just setting the factors equal to 0 and solving for x. So if I have this quantity, x squared plus 4, and I set that equal to 0, I would need to subtract 4 from both sides, and then I would see that x squared is equal to negative 4. If I wanted to solve this equation then, I would have to take the square root of both sides. And if you notice now, I'm trying to take the square root of a negative number, and that's going to lead me to an imaginary solution. And because I'm taking the square root of both sides, I'd have plus or minus, and then that would actually simplify to 2 times I. And so what it looks like is this extra turning point in the graph that doesn't actually hit the x-axis. And so the correct answer for this next graph, or for this next equation, is going to be G. It's got 2 real and 2 imaginary roots, and that's what this extra turning point is. I know the graph has to turn at some point because my degree is 4, so I know it's got to turn around so that it can cross the x-axis twice. So that doesn't surprise me. It's this extra turning point here where it doesn't hit the x-axis that I know there must be an imaginary root. In fact, they have to come in pairs, and they have to be complex conjugates of each other. So that's why it's a plus or a minus 2i. All right, and the next to last one, we've got actually 4 factors of x again, 1, 2, 3, 4. They're all single roots, so that's going to be easy to identify. I think it's probably obvious at this point that the correct answer is going to be C, but let's show why. This single factor of x means that x is 0. If I see an x plus 2, that means that x is going to be negative 2. If I see an x plus 3, that means that x is going to be negative 3. And if I see x minus 4, that means that x is going to be 4. If I wanted to write this in set notation, I could write it like this: 0, negative 2, negative 3, and 4. So that goes back to what you saw in a previous problem. And if I look at the graph of C, I can see that it crosses at 0, it crosses at negative 2, negative 3, and positive 4. And then the very last one, I think, is pretty obvious because we only have one left to choose from, has got to be f. And if I take a look at my roots, again, I have this factor of x, which corresponds to a root of 0. And then I've got x minus 3, the quantity, squared. So that means that x equals 3 is a double root. And if I add all those roots together, I know I'm dealing with a degree of 3. My leading coefficient is positive, so I'm looking for an s that increases, which obviously is going to be the graph of f. It's the only one that is an s that increases. So that's one way that I know I'm right. And if I look, I can see that at x equals 0, the graph passes straight through. It doesn't turn around, and it doesn't change concavity, so it's a single root. And I can see that at x equals 3, since the graph turns around, at that point, it's a double root. So those are several different ways that I can verify that I've matched these equations to their graphs correctly. And I believe that's it. Yep, we're all done. So I hope that this was helpful. Again, you can rewind and rewatch anytime you want. These videos are also posted on the goodies drive at school if you have trouble accessing YouTube at school. And just talk to your teacher about getting some extra help during Bulldog Block if you need it. Good luck to everyone. We're here if you need us.